Alright, good day everyone. So welcome back to my YouTube channel and this is Kasaligan Vlogs. Today we will be talking about permutations and I hope everyone you will have to watch the duration of this discussion. So let us first define factorials. Factorials are used extensively in mathematics. Let k be a positive integer. Then the product of the first k positive integers is called the k factorial. And it is denoted by the symbol k factorial. So thus, when k factorial is equal to k times k minus 1 times k minus 2, that is equal to 3 times 2 times 1 up to 1. So take note that 0 factorial is the same as 1 factorial. So 0 factorial is equal to 1 and 1 factorial is equal to 1. So for example, 5 factorial, so we'll have to state that 1 as 5 times 4 times 3 times 2 times 1 is equal to 120. So every arrangement in order of a set of things is called permutations. So it refers to a set of objects in arrangement of the said object in definite order. Thus, the set of all the letters MSA, if you use all of them, can be arranged in the following orders. Whether we have here MSA, Mass, AMS, SMA, SUM, and ASM. So this is what we call as permutation. Take note, it is with regard to order. So there is an order. So AB is not equal to BA because the order is not the same. So that is what we call as permutation. So there are cases to be followed in permutations. So the first case is permutation of objects taken all together. Example, in how many specific ways can three books, statistics, algebra, and biology, be arranged in a cell? So let us have first this one, statistics, algebra, and biology. We will arrange this one manually so that we could find the number of specific ways that we could arrange statistics, algebra, and biology. So let us have first this one, statistics, algebra, and biology. We have here statistics, biology, and algebra. The next arrangement is algebra, statistics, and biology. And we have also the next arrangement is algebra, biology, and statistics. And biology, statistics, and algebra. And this one is biology, algebra, and statistics. So in this case, we could produce 6 arrangement of this part. So therefore, if we're going to apply the formula, which is permutation of objects taken all together, so therefore we have here statistics, algebra, and biology. So there are, and the number of n is 3. So therefore, 3 factorial is equal to 3 times 2 times 1 is equal to 6. So therefore, in manual and in permutations taken all together, we have here the same answer. So determine the number of permutations of letters of the word simple if all are taken at a time. So we have here, we're just going to compute this one as 6 factorial because the number of letters here is rather is 1, 2, 3, 4, 5, and 6. So 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. So we have here 720 permutations that we could produce out of the word simple if all are taken at a time. So we have here, so if we're going to compute that one in 6 factorial, we can see in a calculator like this, 6 factorial. So let us proceed with example number 2, or case number 2. In case number 2, permutation of objects taken r at a time. So NPR is equal to n factorial over n minus r quantity factorial. So let us have first, before proceeding with the word formality, let us consider this one. Okay, let us consider the word pet. If the word pet is taken at a time, twice at a time, or two at a time, so we could have the arrangements as PE, EP, and this one is PT, TP, or this one is ET and TE. So if the word pet is taken two at a time, so we could produce six permutations here or arrangement. So PT, PE, EP, PT, TP, ET, and TE. So applying the formula, we have here 3 taken 2 is equal to 3 factorial over 3 minus 2 factorial. So therefore, we have here 3 times 2 times 1 over. We have here 3 minus 2 that is equal to 1. And 1 factorial is equal to 1. So therefore, we have here 6. So there are 6, so complete here. There are also 6 here when we take pet 2 at a time. So we could have apply also the fundamental principle of counting. We have here this one. Okay, so we have here the pet taken two at a time. So therefore, so the word pet, 3 letters. So therefore, 3 times 2, that is equal to 6. So taken two at a time. So because there are 2 letters we need to get from the word pet. So 3, the first position is complete, but we need to not to repeat the second one, so therefore 2. Or shall we say we have here PE, EP, so then the next position will not be repeated, so therefore we need to scratch. So there are two possibles now, so we have here 6. So in this case, how many 5-letter words can be formed with the word formality? So by the use of formula, so we have here Formality. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll just have to here 9 permutation of 5. So 9 factorial over 9 minus 5 factorial. So in this case, we have here 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over, we have here 9 minus 5, this 4 factorial, this is 4 times 3 times 2 times 1. So cancel this part. So we have here the answer is, when we multiply that one, we have here 1,520 5-letter words can be formed. So if we're going to apply this fundamental, we have here 5 letters. So let us consider 5-letter word. So 1, 2, 3, 4, 5. So there are 9 words, 9 letters in formality. So therefore we have here 9 times 8 times 7 times 6 and times 5. If we multiply this one, we can produce 1,500 5-letter words in this word formality. So let us consider example letter B. In example letter B, how many 4-letter permutations can be formed from the letters in the word heptagon? So 1, 2, 3, 4, 5, 6, 7, 8. So 8 permutation of 4. So by calculator, So we can produce that one as 8 factorial over, we have here 8 minus 4 factorial. So we have here 8 times 7 times 5 times 6 times 4 times 3 times 2 times 1 over, there is 4 factorial. So 4 times 3 times 2 times 1. So cancel this part. We have here, okay, so 4 letter. So in this case, we have here 7, and this is 6 rather. Here's 6 times 5. 8 times 7 times 6 times 5. And cancel this part. So we have here, the remaining is 8 times 7 times 6 other times 5. That is equal to, when we get the permutation is 8 permutation, we have here 8p, 8, 1, 2, 3, 4, 5, 6, 7, 8. So 8 permutation. So by the use of calculator, so let's have calculator here. 8 times 7 times 6. So by the use of calculator, so we have here the answer 8, 8 shift permutation. So the heptagon is 1, 2, 3, 4, 5, 6, 7, 8. So again, heptagon. So there are 8. So we have here again 1, 2, 3, 4, 5, 6, 7, 8. So 8 permutation 4, we have 1680. So the same concept with this one. If you take 4 letter in heptagon 1, 2, 3, 4, 5, 6, 7, 8. So we have here 8. And this there are 4. So 8 times 7 times 6 and times 5. If we multiply this one, we have here 1680. And that's it for heptagon. Okay, so let's proceed with number letter C. A school musical director can select 2 musical plays to present next year. One will be presented in fall and one will be presented in spring. If she has to pick from, how many different possibles are there? So we have here 9 permutation of 2. So 9 factorial over 9 minus 2 factorial. So we have here 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But you could use calculator. Just click here, 9 permutation of 2, that is equal to like this. So what is 9 permutation of 2? That's equal to 72. So if we're going to compute it manually like this, so this will become 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 and times 1. So cancel this part from here 7. So therefore we have here 72 ways. The same as here by this principle. So we have here 9 and we could not select anymore the other one. If we selected here in this position times 8, we have here 72 uh, ways or possibilities. So letter D, the advertising director for a television show. Television show has 7 ads to use in the program. If she selects one of them for the opening of the show, one for the middle of the show, and one for the ending of the show, how many possible ways can this be accomplished? So in this case, we have here, we have 7, and we need to have select one at the opening, and one in the middle, and one in the ending. So by the use of permutation, so we have here 7 permutation of 3 is equal to 7 factorial over 7 minus 3 factorial, that is equal to 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 and times 1 over, this is 4 factorial 4 times 3 times 2 times 1. So cancel this part. So we have here 7 times 6 times 5, that is equal to 210. Okay, so that's all for this part. So let us next have the permutation of n objects, not all distinct. So this is the formula for not all distinct. When you say not all distinct, there are letters or the same of the kind. So not all distinct. So the formula is n factorial over n1 factorial, n2 factorial, and so on. We have nk factorial. So before proceeding with the examples or here in the problems, let us have apply first in a situation first, not so having many letters. So let us have first an permutation of n objects, not all distinct. Let us have an example of the word egg. Okay, the word egg can be rearranged in how many permutation? So let us have egg. So next is G, EG, and the next one is G, GE. So are there other ways for this one? So let us have three. So by the use of the formula, permutation is equal to, so how many letters are repeated here? G. So how many are repeated? We have 2. So therefore this is 2 factorial. So this one is the repeated letters and the number of letters being uh, repeated also. So example G, we have here the number of letters, the letters that has been repeated. So therefore 3 factorial, because the word egg has 3 letters, over 2 factorial, because G is being repeated twice. So we have here 3 times 2 times 1 over 2 times 1. So therefore we have 3. So by the use of this one, by uh, tamban-tamban, or shall we say this is a manual process, we have here 1, 2, and 3. So therefore, if we're going to apply in the word concoction, so in how many permutations can be made with the word concoction? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 factorials here, but the repeated. So let us have letter C, which is how many letters C? 1, 2, 3. So therefore, this is 3 factorial. And the letter O. So letter O, 1, 2, and 3. So this is 3 factorial. How about letter N? In letter N, so 1, 2. So therefore, this is 2 factorial. So by the use of the permutations and the formula, we have here 10 factorial over 3 factorial times 3 factorial times 2 factorial. So if we're going to compute that one using your calculator, so it will produce 50,400, okay, 400 permutations or ways. So 50,400. So if we're going to apply by the use of calculator, so 10 factorial over 3 factorial times 3 factorial times 2 factorial. So let us have probability. The word probability has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So therefore this is 11 factorial. So the letter that is being repeated in probability is B, which is 2 factorial. There are 2. And I, we have here 2 factorial. So by the use of the formula, I guess no other letter that has been repeated. So by the use of formula, 11 factorial over 2 factorial times 2 factorial. So if we're going to multiply 11 factorial over 2 factorial, that is equal to, let us compute. Okay, we have here 11 shift factorial over 2 shift factorial times 2 shift factorial. That's equal to 9, 9, 7, 9, 2,000, 200, rather. 9,979,200 ways that you could arrange the letters probability. So next is statistics. Statistics, we can arrange the letters in the word statistics. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 factorial here. But the repeated are the following. The repeated is S. So in letter S, we have here 1, 2, 3. You have 3 factorial. For T, for T, we have here T is equal to 3 factorial. So 1, 2, and 3. So we have here 3 factorial. For we have here I. So in I, there are 2 letters. So therefore, I is 2 factorial. So if we're going to compute this one, we have here permutation is equal to 10 factorial over, we have here 3 factorial times 3 factorial times 2 factorial. So the answer of this one is the same as in concoction, which is 50,400 ways we can arrange the letters of the word statistics. Next, we have here problem number 4. If a coin is tossed 6 times, how many different outcomes consisting of 4 heads and 2 tails are there? Okay, so we have here in permutations, by the use of these permutations, that not all these things, we could apply this concept. If the coin is tossed 6 times, how many different outcomes consisting of 4 heads and 2 tails? So we have here, we could apply 6. We have here 4 plus 2 here, we have 6. Since this is repeated, and we will consider as repetition, and this is repetition, so we have 6 factorial over 4 factorial times 2 factorial. By the use of calculator, we have here, okay, 15 different outcomes we could produce out of this problem. Next is a stockbroker wants to assign 20 clients equally to 4 in each sales people. In how many different ways can this be done? So the word for of each sale paper equally. So therefore, if there are 20, so therefore we can divide it by 5. So permutation of objects is 20 factorial over, since we are going to divide it by 5, 4 equally, so divide 4 to 4 people. So there are 5 factorial times 5 factorial times 5 factorial times 5 factorial. So if we're going to compute this one using your calculator, okay, by the use of calculator, okay, let's have 20 shift factorial over, okay, let's compute, 5 factorial times 5 factorial times 5 factorial times 5 factorial is equal to 11,732,745,024 wings. So that's it for this problem. And for number 6, a shopping mall has a straight row of 5 flagpoles at its main entrance plaza. It has 3 identical green flags, 2 identical yellow flags. How many distinct arrangement of the flags and the flags are possible? So if we're going to compute this one, P is equal to, we have here 5 factorial over, this one is um, identical, so therefore 3 factorial times 2 factorial. So therefore, by the use of calculator, we have here, okay, let us compute this one. So 5 factorial, shift 5 factorial over, we have 3 factorial times 2 factorial. The answer is, okay, 10. Okay, 10. So again, 5 factorial over 3 factorial. The answer is 10. So these are the cases for permutation number, this part, number 3. So let's proceed with circular permutation. The last one is circular permutation. In how many ways 8 guests be seated in a round table? But before to answer this one, let us have first this concept of circular permutation. So in circular permutation, so let us have this one. So let us have this one as A, B, and C. Since this is a circular permutation, so we have to test first in a clockwise direction. So therefore, this is the first arrangement. And in this one, the next position, if you're going to arrange this one not repeated in the same direction, we could say that this would be A, C, and this one is letter A. So this is letter B. So this is BA. So this is BA is not in the same direction with AB. So this is second position. Can we have another position? So in this case, if we're going to look at here, B is uh, steady. So it is in a fixed position. So therefore, our circular permutation is n minus 1 factorial. So let us have first one. So since this is 3 fac factorial, so in permutations, other in circular permutations, P is equal to 3 minus 1 factorial, that I have 3 times 2, that is equal to 6. Or rather, 3 minus 1, that is equal to 2. Okay, this one is 2 factorial, that is equal to 2. So there are two positions here. Sorry for that. So again, 3 minus 1 factorial is equal to 2 factorial. So 2 factorial is equal to 2. So therefore, we could prove that this one is correct. Okay, so in how many ways that can 8 guests be seated in a round table? So therefore, we can have permutation is equal to 8 minus 1 factorial. So therefore, we have here 8 minus 1 factorial of 7 factorial. The answer is, by the use of calculator, the answer is 5,040 ways. Okay, that's it for this time. So try this at home. So compute the three problems for this Fridays about permutations. Thank you for watching, and I hope everyone you learned something from the discussion today. Thank you, and God bless everyone.